Welcome to ColeSoft's cXDC class. My name is David Cole, and I am President of ColeSoft Marketing and Chief Architect for cXDC. In this series of classes, you will learn everything you need to know to get started debugging your C programs. But before I get started, let me explain how this is going to work. The class will be guided by several highly animated presentations that can be viewed either as videos on YouTube or as PowerPoints driven by a live instructor. When driven by an instructor, he will let the presentation run a couple or few pages at a time, and then pause so that he can make comments and you can ask questions. But if you have a question at any point, please do not think you have to wait for me to pause before asking it. I encourage you to ask your questions as we go along. Let's get started. In this class, we are going to cover everything you need to know to use cXDC within cXDC. We will start with learning cXDC terminology and concepts. We will move on to describe the JCL changes needed for creating dwarf data, and then we'll discuss the various ways to start a debugging session. Then we will discuss understanding and navigating cXDC displays, setting up and using dwarf data to build source code and variable maps, displaying C source code in storage, and setting hooks and traps. Then we'll talk about stepping, tracing, and trapping program execution, displaying and zapping C variables, and understanding variable scopes and stack frames. We will continue with understanding and using session profiles. And finally, we will end with understanding and navigating Builtin Help. Let's start with cXDC terminology and concepts. Okay, so what is the relationship between cXDC and zXDC? Basically, cXDC is a component of zXDC. It's what we call a licensed feature. zXDC is composed of 4 licensed features. There is a required feature known as base XDC. This contains the infrastructure that is available throughout zXDC, such things as display management, session profile support, ZOS and hardware knowledge and displays, a disassembler, simple symbol creation and management. Such symbols are called equates. Load module mapping support. XDC knows how to load link edit maps, also known as binder maps, for both load modules and program objects. Session logging, and support for debugging both in batch and TSO environments. There is an auth XDC feature, needed if you want to debug programs running authorized. There is an ASM XDC feature for debugging assembler programs. It understands building assembler program maps from AData and SIMData. It also lets you build, copy, and manipulate dissect maps for control blocks and data areas. Finally, there is the cXDC feature for debugging XLC, C++, and Metal C programs. It knows how to build C program maps from dwarf data and source files. It also thoroughly understands C variables, where to find them, how to display them, and how to zap them. I want to speak briefly about C source code statements and the machine instructions that underlie them. Of course, when a C program is loaded into storage, it's just data. Raw, hex, data. Definitely not source code. But there are 2 things that turn raw data into executable code. The first is that the data must be valid as machine code. Second, the CPU's next instruction pointer must be able to run through it. The next instruction pointer is part of something called the program status word, or PSW for short. In this case, cXDC has frozen the PSW at a load address instruction. But of course, what we're looking at here is not source code. It's only the machine code that the source code was compiled into. But when mapping is properly set up, cXDC will automatically read dwarf files, source files, and program objects to build source image maps and apply them to the code in storage. Then when you display the code, you will see it as C, C++, or Metal C program statements. The underlying machine code is still there, of course, and cXDC will show it to you if you ask. But you don't have to see it if you don't want to. Alright, moving along now. Let me say a few words about load modules and program objects. Load modules and program objects are the final outputs of the program build process. The compiler translates source code into object modules. The binder then takes object modules from one or more compilations and assemblies and combines them into load modules or program objects. The program object is now ready for loading into storage for execution. Program objects are like load modules, but on steroids. Load modules are an ancient technology from the 1960s. Program objects, on the other hand, have existed for only about a decade and a half. But the differences are not important to this class, other than to say, to make use of the full capabilities of C programming, you generally need a program object. Typically, a C program's program object contains a lot more than just the compiled C code. Sure, the C code's in there, but there's a lot more. For one thing, there's prologue code that comes before the program's first statement. And then there's epilogue code that follows the compiled code. And there's also a lot of C and language environment support routines of all sorts. This schematic shows a fairly simple case where one source program is compiled and bound into one program object. But of course, more complexity is possible. For starters, the program object can contain C programs from more than one compilation. But why just C? Why not throw in some COBOL and even assembler? And whatever else you like, Fortran, PO1, more C, whatever. And of course, there will be scads of support routines thrown in by the language environment. The point is, cXDC uses binder maps to understand all this. Without binder maps, program objects look like this. With binder maps, cXDC knows what's inside. One thing you may have noticed in the prior slide or few, I've thrown the word csect around a bit. So, what is a control section? To the binder, a csect is the smallest thing in a program object that can be independently added, deleted, renamed, and generally manipulated. These are all csects. They are the building blocks of program objects. To a C programmer, a csect is just a compilation unit. When you compile one source module, you get one csect. When you compile two, you get two. Throughout cXDC, we will use the term csect, not compilation unit. Now a few words about mapping, about binder maps and program maps and how they work together in cXDC. Maps convey internal information about program objects, source code, and variables. Without maps, cXDC does not know what is inside program objects. And when looking at code, about all cXDC can do is disassemble storage. But when cXDC loads a binder map, suddenly it knows what's inside the program object. And when program maps are loaded, cXDC can suddenly show your source code images, not just disassembled machine code. So cXDC needs both binder maps and program maps. When everything is set up right, cXDC loads these maps automatically. Stepping versus tracing versus trapping. Stepping and tracing both allow program execution to proceed, but only for a little ways before execution is recaptured and control is returned to cXDC. Trapping, on the other hand, lets you choose where to stop execution. Stepping is C-oriented. It moves execution from one language statement to another. It steps you from one C statement to the next, to the next. Tracing, on the other hand, is machine language oriented. It steps you one instruction at a time, or a few depending on the operands you use. Getting back to the C code, one thing to notice here, not every C statement gives rise to its own individual set of machine instructions. In reality, a lot of C statements do not generate machine code at all. Instead, they just provide information to the compiler for use elsewhere. This is why multiple C statements often show the same code offset. So when a statement does not have underlying machine code, it is not possible to stop execution solely on that statement. This is why cXDC often highlights multiple statements as being, quote, the current statement. So much for stepping. Now let's talk about trapping. Trapping is different. Trapping lets you tell cXDC where you want execution to stop. Here I am stopped at statement number 108. Suppose I want to let the program run and stop at number 134. First, I'll use a trap command to tell cXDC where I want execution to stop. Then I'll use a go command to release execution and let the program run until it hits the trap. Be aware that there are two kinds of traps: temporary traps and persistent traps. Temporary traps are one-shot traps. When execution reaches them, they are automatically removed. They are set with the trap command. And then there are persistent traps. They are also known as permanent traps. No matter how often execution reaches them, they remain in place. They are set with the at command. They can only be removed by an off command. In general, you should use the trap command unless you have a specific reason to keep the trap around for a while. In that case, you should use the at command. Now here's an important question. What's a hook, and what's a trap, and what's the difference? Both hooks and traps interrupt program execution, and both are intended to cause control to pass from the program over to cXDC. However, traps require that a cXDC debugging session already be properly set up, while hooks do not. A hook will create a debugging session if it has to. cXDC can do what it does because it is a recovery routine. So it is pretty important to understand at least a little bit about how recovery routines work. Formally, as far as ZOS is concerned, ZXDC is a recovery routine, also known as an ABN handler or eStay routine. A recovery routine is the underlying ZOS infrastructure that is at the heart of the handling of events called signals in C and exceptions in C++. Recovery routines receive control when illegal or failing actions are attempted, such as the execution of unsupported instructions, which causes OC1s, or referencing inaccessible storage, which causes OC4s. When no recovery routines exist, ABNs cause program terminations, possibly along with storage dumps. LE has a recovery routine to intercept ABNs and route control to signal or exception handlers. ZXDC is a recovery routine that supports debugging. It can be set up either as an eStay type routine for most usages, or as an FRR for certain highly constrained supervisor environments. For C debugging, ZXDC will almost always be the type of eStay routine known as an eStay X. When an abend occurs, ZXDC must receive control first, ahead of LE's recovery routine. Setting this up is called establishing a debugging session. Suppose I have a program that is making a set of changes to a database. Suppose that an abend occurs before all those changes have been hardened. What happens now? Well, if the program had set up an eStay routine, then that routine would be given control and it could back out the uncommitted changes. In general, recovery routines work in partnership with their owners, the routines that set them up. A recovery routine's job is first to prevent the abend from corrupting anything important. Second, to recover from issues that it understands. Third, to provide for dumps and other diagnostics about things it doesn't understand. The point is, eStays and the programs they protect work together. In particular, the mandate of an eStay is to protect only the program that created it, and to that end, an eStay generally has detailed knowledge of the risks and needs only of its owning program. Of course, programs call programs call programs call programs. And then they return. So at any given moment in time, there is likely to be any number of recovery routines in existence, ordered from oldest to newest. So what happens when a ZXDC trap is executed? Remember, traps are just invalid opcodes. As far as the system is concerned, they're nothing but plain old OC1s. Well, if the newest recovery routine is ZXDC, then he will receive control, and he will recognize that this particular OC1 is actually a trap, and he will remove the trap and repair the code, and he will present a display to you and ask, what's next? But if some other routine should happen to come along and establish its own recovery routine that is newer than ZXDC, then it all falls apart. That's because this newer routine will see the OC1 before ZXDC does, and he won't know what to do with it. And things will break in wild and confusing ways. To fix this sort of problem, you need to set a hook, not a trap. Then when execution reaches the hook, a long jump will be made to a hook support routine, which will remove the hook, create a newest recovery routine for ZXDC to run in, and finally hit an internal trap to pass control to XDC. ZXDC can be used to debug programs running either in the batch or in TSO. Batch means both batch jobs and system tasks collectively. Batch debugging requires the server XDC task be running. The server task provides a number of services needed by ZXDC. But for batch debugging, the one that is particularly needed is CS-CDF XDC, also referred to as cross-sysplex CDF. When a debugging session starts in the batch and ZXDC receives control, It connects to cXDC where it waits for a user to talk to. A user may connect from any idle VTAM terminal or from a TSO ISPF panel running on any system in a connected sysplex. It is important to understand that while the user might think that cXDC is running in TSO, it is not. cXDC is running in the batch because that is where the debugging session is. If you don't keep this in mind, then certain aspects of the way in which XDC behaves might seem confusing. It is also possible to debug programs running in TSO. In this case, cXDC is not needed. Instead, cXDC communicates directly with the user terminal using either ISPF display services or full-screen TGETs and tputs. However, most of our customers write products that run as batch jobs or system tasks. So mostly they debug in the batch. Finally, let me mention one of the most important parts of cXDC. It's Builtin Help. The Builtin Help is a rich and comprehensive database of how-to information for cXDC and cXDC. And the help command is just one of the doorways into it. There are others. Every aspect of cXDC is documented, from commands to messages to debugging topics of all sorts, including, of course, help with cXDC. The online help is what computer scientists, God bless them, call a, quote, ordered directed tree structure. I didn't know that. Did you know that? The front page links to a dozen or two subtopics. Subtopics link to sub-subtopics, and so forth, and so on, and so on, and so forth. You can, of course, issue help commands from any command line. You can also use the H shortcut command on certain display lines, such as on any DBC numbered message. The Builtin Help database is quite large and is easy to get lost in. So cXDC has a list help command to help you navigate. These are the names of help topics. Where you see the plus signs, you can use the L shortcut command to display subtopics, and the H shortcut command to display the topics themselves. Finally, check out these shortcut input fields at the far left. They can accept various single-character shortcut commands. Altogether, there are around 24 unique commands that might be used, but there is no shortcut input field that accepts all 24. However, there is one shortcut command that is accepted by all input fields, the question mark. It shows which shortcut commands a given field will accept. Okay, yeah. Well, if this is still just a bunch of mystery letters, just remember you can use an H to get more information about any DBC numbered message, including this one. Okay, that's enough introduction. The next PowerPoint will be about the JCL changes needed for creating dwarf data at compile time. Finally, here are a few links to remember. ColeSoft.com is where you can go to get general information about both cXDC and cXDC, and to find out what our friends think about our products. You can also download products and start trials. You can also download maintenance and temporary licensing keys. And you can reach out to our sales team. XDC.com is the front door for a forum we have on LinkedIn where you can ask questions, get tips, and learn about the latest news and maintenance. If you join this forum, you will receive push notifications about maintenance and new developments. We have a number of training videos on YouTube for both ZXDC and cXDC. And we keep a Facebook presence for less businessy information about ColeSoft and its people. When you need technical support, you can reach us both by the forum and by email and by phone. You will find our people to be both quick and knowledgeable and accommodating. Thank you.